Hello everyone, this is Nityanjali from Sri Venkateswara College of Engineering in Bengaluru, branch EC, subject network analysis, topic explain classification of electrical networks. Classification of electrical networks. This presentation delves into the fundamental classification of electrical networks, exploring different categories based on their properties and behavior. We will examine how these classifications impact circuit analysis, design, and understanding. Let's dive in. Introduction to electrical networks. Basic components. Electrical networks consist of interconnected elements like resistors, capacitors, inductors, and sources. These components define the network's behavior and characteristics. Network analysis. Analyzing electrical networks involves determining voltage, current, and power relationships with the circuits. This analysis helps understand how the network operates and predict its response to various stimuli. Passive versus active networks. Passive networks are made entirely of elements that absorb and dissipate energy such as resistors, capacitors, and inductors. They cannot generate power, so they rely on external sources to function. Active networks. Active networks include components that can generate or amplify energy. These typically involve sources like batteries, generations, or amplifiers which can introduce power into the networks. Linear versus nonlinear networks. Linear networks. In linear networks, the relationship between input and output is directly proportional. This means the output is constant multiple of input regardless of input's magnitude. Nonlinear networks. Nonlinear networks have more complex relationship between input and output where the output is not directly proportional to the input. These networks may exhibit nonlinear behavior such as saturations or distortion. Time variant versus time invariant networks. Time invariant networks. Networks where the characteristics and parameters remain constant over the time are called time invariant. Their behavior is predictable and independent of time. The time variant networks. In contrast, time variant networks have parameters or characteristics that vary with time. These variations can introduce complexities in analysis and prediction of network behavior. Distributed versus lumped parameter networks. Distributed networks like transmission lines have properties distributed continuously throughout the circuit. Analyzing these networks requires considering the continuous nature of the parameters. Lump parameter network is construct have components with concentrated properties. These are commonly used for circuits where components are small and distance between them are negligible. Serial versus parallel networks. Series. Components in the series share the same current but have different voltage drop across them. Parallel. Components in parallel share the same voltage but have different currents flowing through them. Combinations. More complex networks often involve combinations of series and parallel connections requiring careful analysis to understand the overall behavior. Resistive, capacitive, and inductive networks. Resistive networks. These networks are primarily composed of resistors which are resist the flow of current and dissipate energy as heat. Capacitor networks. Networks dominated by capacitors store electrical energy in electric field, affecting the network's responses to the change in voltage. Inductive networks. Inductive networks are primarily made of inductors which store energy in magnetic field influencing the flow of current in response to change in current. Resistive, capacitive, and inductive networks. Real world examples. These network types are fundamental to various technologies. Resistors are used in everything from voltage dividers to current limiters. Capacitors find use in filters, energy storage, and coupling circuits. Inductors are vital in circuits that handle AC currents like motors and transformers. Applications. Understanding these networks types is crucial for designing and analyzing various electrical systems, for simple circuits to complex control systems. Conclusion and key takeaways. Classifying electrical networks is crucial for understanding their behavior and designing appropriate solutions. This framework allows for a systematic approach to analyze, ensuring accurate predictions and efficient circuit design. As you delve deeper into the electrical engineering, remember that these fundamental concepts are the building blocks of the complex systems. Thank you.